we need to have a parametric curve and find where the tangent line is horizontal. So we have x is equal to t squared e to the t, and y is equal to 3 cosine of t. Also, we are on the interval t going from negative pi over 4 to 5 pi over 4. So we want to find the points in rectangular coordinates where the tangent line is horizontal. So remember, the tangent line is given by dy dx, which in our parametric form here is going to instead be dy dt over dx dt. So we have x of t and we have y of t, so that should be pretty simple. So let's do the derivative of dy dt. That's just the derivative of this. 3 cosine t, the derivative of that would be negative 3 sine t. On the bottom we have dx dt, the derivative here. For that we'd have to use the product rule. So we'd get 2t e to the t plus t squared e to the t. So that's the equation we have for the slope of the tangent line. We want to know where this is horizontal. So first, let's factor out everything we can. So our dy dx in terms of t is negative 3 sine t over, so we'd have t e to the t. So what's left here is 2 plus t. So we want to know where the tangent line is horizontal. So where the tangent line is horizontal, meaning the slope is 0. So we want to know, where is this equal to 0? Well, this is going to be equal to 0 whenever the numerator is equal to 0. So where is sine t equal to 0? Sine t equals 0 means that t is going to have to be some integer multiple of pi, including 0. Now we're only from negative pi over 4 to 5 pi over 4 for our range of t's. So the only ones that could possibly work are 0 and pi in our range. Well, let's see what happens when we try this. When we plug in 0, we get 0 on the top, but we also get 0 on the bottom. So that's indeterminate. We don't know if that's equal to 0, and we'll have to do more work to figure that out. For pi, though, sine of pi is 0. The bottom just gives you some positive number, so we do get 0. So this is certainly a point where our tangent line is horizontal. For 0, we're going to have to do more checking. So we really need to do the limit as t approaches 0 of this, because we're trying to solve this as an indeterminate form. Now, you could do L'Hopital's rule here, but that would be kind of extreme because the bottom would be very difficult to do. Instead, I'm going to separate the sine t over t from the rest of it. Oops, we already had a t over there. So we'd have e to the t 2 plus t. So this product is the same thing as this, but the reason I did that is because the limit as t goes to 0 of sine t over t is a trig identity that you should know. Sine t over t as t goes to 0 is just 1. So this is really equivalent to negative 3 over e to the t 2 plus t when t is close to 0. If we plug in 0 here, we get negative 3 halves, which is clearly not 0. So as t gets to 0, that slope is not 0. So our only point where the tangent line was horizontal is when t equals pi. But that wasn't exactly the question, because the question asked us what are the rectangular coordinates. So we need the x, y, meaning we need to plug t back into this. So t equals pi corresponds to an x coordinate of pi squared e to the pi. And a y coordinate, 3 cosine pi. Cosine of pi is negative 1, so we'd have negative 3. So that point right there would be the rectangular coordinates of where the tangent line is horizontal to this graph. For the second part of problem number 4, we need to determine the second derivative. So I've copied the derivative we got from the first part, and we're trying to find not only the value of it, but the concavity at the point that we were talking about. Remember, the point that we were talking about in the previous problem, we resulted in t equals pi. So we need to take, in order to find the second derivative, we need to take the derivative of that. So recall that the way you do this in parametric is a little bit different though, so that if you want to do the second derivative but you only have functions that are in terms of t, you need to do the derivative dt of your first derivative, again divided by dx dt. So basically we need to take the derivative of this and divide it by dx dt. But remember, dx dt was actually just this part in the first place, so we're going to be just dividing by another copy of that. No reason to do that work again. And we can kind of do another shortcut here because we know that taking the derivative of this is going to involve the quotient rule. What happens in the quotient rule is that you have to divide by the denominator squared. So no matter what we get for the second derivative, we're going to get t e to the t 2 plus t all squared. And then we're dividing by it again because it is dx dt. So what I'm getting at here is that on the denominator, we're going to have this whole thing to the third power because we're going to have 3 copies of it. And then on the numerator is just going to be whatever the numerator of this quotient rule was. So I'm going to write these all to the third power of what they were. So the numerator is just going to be the numerator of the quotient rule here. So remember, for the quotient rule, we take the derivative of the top, negative 3 cosine t, times the bottom, t e to the t 2 plus t, times the derivative of the bottom times the top. So when we do the derivative of the bottom, it's going to be in our best interests to distribute this so that we don't have to do the product rule, or so that the product rule is a little bit clearer. Before I factored this out, it looked like this: 2t e to the t plus t squared e to the t. So when we take the derivative of this, we're going to have to do the product rule twice. I'm probably going to need more room. So let me rewrite that a little bit over here. So again, when we do the derivative of the top times the bottom minus the derivative of the bottom. So here we're going to have 2e to the t plus 2t e to the t. That's the product rule of this part. Product rule of this part is going to be plus 2t e to the t plus t squared e to the t. And then we multiply by the top, which was negative 3 sine t. But since we're already subtracting, we could just make this a plus and put 3 sine t. So that looks pretty gross, and it is. But there's a lot we can do to simplify it, because we know that we're looking at when t is equal to pi. So over here, when we would do sine of pi, we would get 0, which makes that entire term 0. So we can actually disregard that entire term. And when cosine of t, and cosine of t when t equals pi, we would get cosine of pi, which is negative 1. That would just make this 3. Now I'm doing a little bit unorthodox method here, what you shouldn't really do technically, because I plugged in I plugged in pi for t only for a couple of things and not for all of it at once, which is technically what you should do, but I'm just doing this to show you that something else is going to cancel also, because we have t e to the t 2 plus t, we have that cubed here at the bottom. So this all is going to cancel out and lower all these powers to 2's. So really we get down to this. So that's much simpler than what we started with. And that's as simplified as we can get. And now we can just plug in t equals pi for the rest of it. And we would get 3 over pi squared e to the 2 pi 2 plus pi squared. And that you don't need to do anything else with. That's as simplified as it's going to get, because you have e to the 2 pi squared. Nothing else needs to be done there. And that is your answer for what the value of the second derivative is at t equals pi. So the last part, it says, what is the concavity? Well, remember that the concavity only depends on the sign of this. And we have pi squared e to the 2 pi 2 plus pi squared. That's all positive. And of course 3 is positive. So this is just positive, which means that we have that our graph is concave up at this point t equals pi, which corresponded to the point pi squared e to the pi negative 3 in rectangular that we got from part 1. So that answers this question here then. This is our value of our second derivative, and that means that it's concave up. And the last problem on the free response, number 5, we have a couple of different things. We need to graph and then find an area of polar graphs. So we have two graphs here. We have r1 squared equals 10 sine 2 theta. And then our r2 is just the square root of 5. So those are our two polar graphs. So first we need to graph these and label the points. We have a couple special points and lines of intersection. So if we're to graph this here, so first let's do r2, because that's just a circle. We have r equals a constant, the circle with radius square root of 5. So this is r equals square root of 5. So the next graph, this is one of our special forms. This is one of the limestone graphs. R squared equals 10 sine 2 theta. Remember, we have anything squared equals constant times sine 2 theta. We get the double leaf shape, and it's going to be in the first and third quadrants because this is positive. So what we need to figure out is how far past it does it go. The easiest way to do that is the maximum that it could be is if sine was equal to 1. And then we'd have r squared equals 10, which means the radius is square root of 10. So the furthest point out on this leaf has an r value of square root of 10. And this would be at pi over 4, obviously. So then we have the same shape down here. And this one is square root of 10. And we have 5 pi over 4. So what we need to figure out now is a couple of special points. So it says graph them, we did that. Label the point on R1 where theta equals pi over 4. So that's the point that I just graphed there at the end. When theta equals pi over 4 and R1, we have this maximum point, the very tip of that leaf. And the radius of that is square root of 10. So the point on R2 where theta equals 0, well, that's just the right point here on this circle. What's our radius? It's square root of 5, because that's what the radius is of the whole circle. And our theta is 0. So that's another special point. And we need the lines of intersection. So our lines of intersection are going to look like this. And this, approximately. So we just need to figure out what angles those are at. So those angles are going to occur when these two graphs are equal to each other. So 10 sine 2 theta, now keep in mind that's r1 squared, so r1 squared would have to equal r2 squared, so this is going to give us 5, not square root of 5. So where does this happen? Well, this is wherever sine 2 theta is equal to 1/2, which means that 2 theta is equal to either pi over 6, 5 pi over 6. We could continue on because we have a double angle. We technically would have more values, but they're just going to give us the other sides of these lines anyway, so it's not really a big deal. So this line right here is theta equals pi over 6. So you can see 5 pi over 6 actually doesn't exist on this graph because that's part of where this would have given us an imaginary number. So we actually do need to continue. Sorry, that shouldn't be theta equals pi over 6. It's 2 theta equals pi over 6, so that should be pi over 12. Oh, whoops, then that's why this one is actually correct. 5 pi over 6. I forgot to divide by the 2. So when you divide by 2, you get 5 pi over 12, which is still in the first quadrant. So that's what this one is here. We have theta equals 5 pi over 12. And then what I was saying before was correct. If you went further and divided by 2 pi, you would just get the opposite sides of those lines. So those are our two lines of intersection and the two special points that they wanted us to graph. So the second part, the last part here, is find the area in the first quadrant which lies inside of R1 and outside of R2. So we're looking for this area right here. Outside of the circle, but inside of the limacone, and first quadrant only. So we're going back to our finding area between polar curves formula. So remember that our area is 1/2 the integral from a to b. In this case, r1 squared minus r2 squared, because we're finding the area between two curves. So we have to use the outer curve and the inner curve. So our outer curve is r1, and our inner curve is r2, because of how our graph is set up there. And we know that it's bounded by these lines of intersection, pi over 12 to 5 pi over 12, so that must be our bounds. And then, other than that, we're good to go. There's no real point to doing a symmetry perspective here, because your area is not very large in the first place. And we have one clearly defined function for the outer and the inner. So our area is going to be 1/2 the integral from pi over 12 to 5 pi over 12. Those are our bounds of integration. Now r1 squared, we already have r1 squared, so we don't have to square that. We just get 10 sine 2 theta. And then we have to subtract r2 squared. Well, r2 squared would just be 5 d theta. Before we evaluate this, we could pull a 5 out, since both of these have a 5 in common. So we get a equals 5/2 from pi over 12 to 5 pi over 12. We get 2 sine 2 theta minus 1. So from there, that's the easiest spot for us to do the anti-differentiation. So we need to do the integrals of those there. So if we take the antiderivative of sine 2 theta, that would be negative cosine. Well, let me actually write the 5/2 first. That would be negative cosine 2 theta. Let's leave the 2 there. Negative cosine 2 theta divided by 2. Remember, when you do the antiderivative of chain rule U substitution with a constant, you divide by that. And then we'd have minus theta. And we're going from pi over 12, pi over 12. Minus theta because we're taking the antiderivative of 1 with respect to theta. So you can see here that these 2's cancel out. So now we just need to plug in our values and do the fundamental theorem of calculus. So 5 pi over 12, we would get 5/2 times. So here we're going to get negative cosine of 2 times 5 pi over 12 will give us 5 pi over 6 minus 5 pi over 12, because then we just have theta. Then we would subtract now when we plug in pi over 12, so we would get negative cosine pi over 12 times 2 would give us pi over 6, and then we have minus pi over 12. Remember, this whole thing was times 5 halves also. So that was top plugged in minus bottom plugged in. Let's see what we get then. So cosine of 5 pi over 6 is root 3 over 2, but it's negative because 5 pi over 6 is in the second quadrant where cosine is negative. So but we already have a negative in front of it. So that ends up just being root 3 over 2. We have minus 5 pi over 12. Now I'm just going to distribute this negative here. So cosine of pi over 6 is positive root 3 over 2. But we have minus and negative, so we're still just doing positive root 3 over 2. And then we have minus negative pi over 12, so we have plus pi over 12. So that's with distributing our negatives and everything. So root 3 over 2 plus root 3 over 2 is 2 root 3 over 2, or in other words, just root 3. And what do we have here? We have negative 5 pi over 12 plus pi over 12. That would give us negative 4 pi over 12, which is negative pi over 3. And we could leave it like that. You could distribute the 5 halves if you like, but this is perfectly fine. So this gives us the area up here under that limestone but above the circle. So again, that's another application of just using the area between two polar graphs. And in this case, just using your basic integrals. Nothing fancy on this one.